Let us work on a few examples to understand what that means. First, please pause and read this question. Here, what we already know is the average commute distance in Ontario, which is 9 kilometers. And the standard deviation is 1.5 kilometers. And these are the population parameters. For the sample, which is in Mississauga, we sampled 225 people, so the sample size is 225. And the average is 9.3 kilometers. Now we want to know if the mean in Mississauga is different from the population of Ontario at a statistical significant level. And this is a one-sample difference of mean test. The first step is to state the null and alternate hypothesis. In null hypothesis, we always indicate that there is no difference exists. And here, we are evaluating the parameter mean. So we are stating that there is no difference between the mean in the population and the mean in the sample. And we can write it as this. Null hypothesis can be denoted as H0, and mu is the population mean, and mu H is the hypothesized population mean. So we write it like mu equals to mu H. The alternate hypothesis or alternative hypothesis can be denoted as H1 or HA. It indicates that a difference does exist. So it is the converse of the null hypothesis. But there are different conditions for the null hypothesis. Either the mu doesn't equal to mu H. So in this case, anything that is not equal, then we can reject the null hypothesis. And this is two-tailed because this is non-directional. So either less than or more than, we can consider that the mu does not equal to mu H. And this is a certain level between around this mean towards the left and the right. There's a range that we can accept that we think it is equal. Anything that is below or above is not equal. Or it can be one-tailed towards the right. So in this case, our question is the mean actually larger than the hypothesized population mean? Or the other one-tail is the lower part, and the mean is actually less than the hypothesized population's mean. So looking back at our question, we know that our hypothesized mean is 9.0 kilometers. So we can write our null hypothesis as mu equals to 9.0 kilometers. And in the question, we are only asking whether it is different from the mean. So it is non-directional. So we use mu does not equal to 9.0 kilometers, and it is two-tailed. Or you can write these in the words like this. H0 is the mean distance in the Mississauga is equal to the commute distance in Ontario. HA, the alternative hypothesis, is that the Mississauga people have a different commute distance from the commute distance in Ontario. Our result may either be beyond the range that we accept or within the range. So we can either reject or not reject the null hypothesis. But it doesn't mean that we are absolutely correct by making this conclusion. Sometimes we can be wrong. And there are two types of errors can occur. Type 1 error is rejecting the null hypothesis when it is true. or we accepting the alternate hypothesis when it is false. This is like when a man gets a pregnant test, it is tested positive. This is false positive. Type 2 error is accepting the null hypothesis when it is false, or failing to accept the null alternate hypothesis when it is true. The second step is to select an appropriate statistical test and calculate test statistics. And here, since our question states that it is a normal distribution, and we have already known the population parameters, including the mean and standard deviation, and our data type is ratio, so we choose z-test. Before we make the final choice of z-test, we need to look at the sample size. If the sample size is larger than 30, then we choose z-test for sure. But if the sample size is less than 30, then we may need to opt for the t-test. And these are the equations for the z-test and t-test. Because in the t-test, we don't know the population standard deviation, so we estimate this through the sample standard deviation. So with all the parameters in the question, we can put them into this equation. So z equals to the mean sample, or the sample mean, which is 9.3, minus the population mean, which is 9, divided by the population standard deviation, 1.5 kilometers, divided by the square root of the sample size, which is 225. So we get a z-score of 3. Next step is to choose a level of significance. The level of significance, alpha, is the probability of making the wrong decision when the null hypothesis is true. So it is a type 1 error. The most commonly used level of significance is 0.05. But sometimes we may also use 0.01 or 0.001. It depends on your question. And if our alpha equals to 0.05, it means that the probability of making the wrong decision when the null hypothesis is true is equal to 5%. So we have the 5% chance of committing a type 1 error by choosing the level of significance of 0.05. And for this example, let's use alpha equal to 0.05. Now we have our z-score and level of significance. We can use them to look up critical values and compare to test statistic. And again, there are two types. There can be two-directional or one-directional. And these two tails means that we need to distribute this alpha on both tails. So each tail will take in 0.025. While if it is one directional, then this 0.05 is in one tail only. Under what circumstances do we choose two-tailed or one-tailed test? Let us look at this example. The background information is the same. So last year, 190 out of 603 students dropped out. But for the question 1, the government claims that the dropout rate is 25%. And for second, it is asking or telling you it is less than 25%. And the third is greater than 25%. And to reject each of the claim, we can simply, for the question 1, if any number that is not equal to 25%, then we can reject it. So it can be either less than 25% or larger than 25%. So it is two-tailed test. For the second one, as long as the result is larger than 25%, then we can reject it. So it is one-tailed. For the third question, if it is less than 25%, we can reject the result or reject this claim. So it is also one-tailed test. Now we know the level of measurement, and we know we need to consult with the two-tailed tests. So we can look up the table to find out the critical value to compare against our z-score. Well, with the softwares such as R, SPSS, we can use the program to print an observed statistic and the probability, and then we can use that p-value to compare with the alpha. If it is less than or equal to alpha, then we can reject the null hypothesis. But in this lecture, we are going to use the traditional method, which is to consult a table. The z-value that we are going to look up from the table equals to this one and this one. And then we will compare these z-value with the calculated z-value test statistic. And then we can make a conclusion if the z-value, the calculated z-value, is less than these z-value from the table or higher than these z-value from the table, then we can reject the null hypothesis. If it falls within these consulted z-value, then we can accept the null hypothesis. The commonly used alpha level is 0.05. Therefore, the commonly used critical value equals to 1.96. Now we can look up this table. Z equal to 1.96. We can look up this value, which is 0.9750. And this is this area. And so the area that is above is 1 minus 0.9750, which is 0.025. So this is the lower limit of the right 2.5% tail for this value. And always, when you're looking at up the table, always look at the shaded area. This is this number corresponding to. And then we can have the z-score for this tail, because either side, that is 0.025, this z-score is 1.96. And on the right side, it is positive, and on the left side is it is negative. So the z-value of 1.96 from the table defines the boundary separating the regions of the rejection and non-rejection of the null hypothesis. And the calculated z-value or test statistic, on the other hand, is the value we compare to the boundary z-value to make reject or not reject the null hypothesis. The calculated result, recall, was z equal to 3. So it will be falling around here, within the shaded area, which we will reject the null hypothesis. So the conclusion is that there is sufficient evidence to conclude that the commuting distance for our Mississauga sample is statistically different from the population mean.